All right, so as we approach the end of this course, we're going to put together a lot of the ideas that we've seen so far to get a sense for what's going on in the exciting field of machine learning. Now, we don't have enough time to do justice to a lot of the modern ideas that have emerged, or even to the field as a whole. So the way that we're going to deal with this is we're going to do an overview of some of the basic ideas, and then we're going to focus in on some concepts that we can use towards our capstone pet classification project, and then we're going to wrap up. Okay? So the basic idea in machine learning is to design algorithms that can learn how to perform some kind of task that we're interested in based on data that we've given it. Okay? So there's some constraints there. We have to find this data from somewhere. We need the algorithm to run efficiently. But let's just kind of look at an example. Okay, so maybe the thing I want to do is I want to train an algorithm, okay, and I want to feed in images, and I want to decide whether they're images of a cat or of a dog. Okay, that's it. Maybe that's my simple example. Now, this actually might seem like a really good fit for something we've already learned about, which is binary hypothesis testing. But the problem is, who's going to give us a probability model for cat and dog images? Okay, so there are no good probability models that we have access to for these kinds of images, unlike the scenarios that we've been looking at in detection. Okay, but what we could do is we can collect a data set of example images. Maybe I give you quite a few images of cats and quite a few images of dogs, and your job is to design a decision rule based on those examples. So that's kind of machine learning in a nutshell. All right, well, let's look at a couple of different categories. So one way you can think about this is through the lens of supervised learning. In this case, you'll have a data set that is labeled, meaning that for each example in the data set that you're using for this training process, you have both the desired input and the desired output, okay? And the desired output is what we sometimes will hear called the label, okay? So in the example above, we had cat images and dog images, and that means for every image in our database, someone has gone through and said, this is a cat and this is a dog, and then we can use that to design our decision rule. In contrast, in unsupervised learning, we have a data set, but the data set is unlabeled, okay? Meaning that for each example, we only know the input and we don't actually know the output. So maybe, just to be clear, if I had that same data set, maybe if someone went and stripped out all of the labels, so it doesn't say whether it's a cat or a dog, it's just an image of either, then it would be an unlabeled data set. Okay, so more formally, a data set is a collection of examples, and we're going to write them in this form. So we're going to have x vector and y, okay? And we're going to have n of those examples, so 1 to n for I. And we can think of this vector xi, okay, as a d-dimensional vector. And we're going to use double indexing for this here. And we're going to try to avoid these double indices whenever we can, but sometimes it's useful to write it down explicitly. So you can see that there's the example, which is labeled by I, going from 1 to n, and then the vector inside that vector, it has entries indexed from 1 to d. So then you have indices I, and that runs from, so I runs from 1 to n, and then maybe there's a second index j that runs from 1 to d, which is the overall dimension of the vector. Okay, and usually we'll just try to refer to these in their vector form and avoid that notation, but it is there if we need it. Okay, so we can think of this vector x as an input, okay? And the entries of this input are what we sometimes call features, okay? The features of our data set. In the cat and dog images, you could think of the features as the pixel values. And we can think of y as the desired output, and we sometimes call this the label, as we just mentioned above, okay? So these features are often very correlated with each other, and the problem with that is that now finding a good probability model for them will have to involve in estimating a very high dimensional function that kind of puts all of that together, and that can require many, many examples, and often more examples than we actually have available, okay? So maybe I even have managed to collect thousands or even millions of images, but still that could, estimating the probability distribution might be out of reach. And this phenomenon is sometimes called the curse of dimensionality, all right? And this is referring to the fact that in some settings, the number of examples you would need in order to estimate the probability distribution scales exponentially with the dimension d, or rather the number of features. And in an image, you might have the number of pixels or the size of the image as the dimension, right? So you would have something like 2 to the 4096 for a 64 by 64 image, and that would certainly be outside of your range in terms of number of examples. So let's look at a few example applications of these ideas, okay? And there are many more. I'm just trying to highlight a few ideas. So there's classification. And so in classification, your job is to place each example into a category specified by its label, okay? And this is very similar to detection. We're just trying to put things into the matching hypothesis, but we do not have a probability model. We only have a data set. Visually, what this looks like is maybe I have some positive labels and some negative labels, and I have to design some way of deciding whether a new example is going to be positive or negative. In this case, I just drew a line, and maybe if you're above the line, you're positive, and if you're below the line, you're negative. Sometimes you make mistakes, but it is a decision rule. Okay, and so an example would be these cat and dog images. I'm trying to classify them to be cat or dog. Regression. So this is to use the input values to predict the output value. So use x to predict y and minimize some kind of loss function. An example we've seen before might be mean squared error. So this is very similar to estimation, but again, we don't have a probability model, we just have a data set. All right, so here's a visualization. I have some points, and maybe I try to fit some curve that matches the trend that I see in those points. Okay, an example might be that I'm trying to do something like predict cholesterol levels, and I want to do that only using some other biometric data like height, weight, etc. And a final example, let's talk about clustering. So maybe I want to group the examples that I have into some kind of meaningful clusters, and I want to do this without access to any kind of labels. Okay, so here I have some points, and I draw one cluster and another cluster. And what would be an example of when I'd want to do that? Maybe I have a lot of news articles online and want to automatically classify them into coherent topics like sports, food, etc. And I want to just do that without someone giving me examples of what those topics might look like, right? So, and this is actually something that's done quite successfully, and I encourage you to read more about it if you're interested. Okay, as a first step, what we need to do is gather and maybe even label, if we want labeled data set. So we need a large collection of examples, okay? So somehow we have to get these examples, and those are going to serve as our data set. Now, one of the most important tasks we have to carry out is we need to decide which features we want to include in the data set. So what do we actually, of all the data we could possibly collect, what are the features we actually want to use? And we usually need to put these examples into the same standardized format, right? So for instance, if we're talking about cat and dog images, maybe they should have the same size. So maybe they should be 64 by 64 images, or whatever the size might be. And the problem we'll run into is that labeling examples by hand can become very time consuming. And you can imagine this gets even more expensive if you want to do something that the labeling has to be done by an expert. So if you're trying to classify tumors and you need a radiologist to come and look at those images and actually put the labels, maybe that becomes prohibitively expensive to build a giant database. And you also have to think about privacy concerns and a lot of other things that we're not going to get into here. The main thing I want to point out is that there are many interesting data sets that you can get freely, so you can just download them. And there are lots of repositories and competitions online that make these available. Okay, I'm just going to spell out a few examples, but you can find lots. Okay, so one would be CIFAR 10. So CIFAR 10 is this image classification data set. And so you can see here that there are 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. And it has 80 million tiny images that belong to one of these 10 categories. And so what you can do is try to develop a decision rule that tries to place each image into one of those categories, and then you can use that as part of a larger pipeline for understanding images. There's also a SciFar 100 dataset and lots of different interesting datasets involving images and classification. You can also go and look at Kaggle. That's a website that hosts a lot of interesting competitions, machine learning competitions, and it collects the datasets from these competitions that you can go and download. And they also have a lot of useful tutorials and other resources if that's something that you're interested in, you want to get started. Okay, so I'll just list a few more machine learning repositories. There's the University of California in Irvine repository, the Google Dataset Search Engine, and there's this thing on GitHub that is called the Awesome Public Dataset website. You can go there and has lots of pointers to other resources. Okay, so we're going to go back to understanding some other concepts. So let's talk about dimensionality reduction. So remember, we just introduced this idea of the recursive dimensionality, which means that it can become really challenging to estimate good probability models. And maybe even if we don't want the probability model, even just selecting a good decision rule, if we have a very high dimensional data set. So if we have many, many features, it can become harder for us to make meaningful decisions from those unless we have some way of shrinking that space down. Okay, so one way to do this is to try to transform our data, and we're going to try to transform it from the original high dimensional representation. So it lives in some high dimensional space. We want to move it to a low dimensional space, and we want to do this in a way that we preserve the important relationships that exist between our examples. Now that's kind of, that varies between application to application, but one way to think about this is if the cat images were originally close to the cat images in some, with respect to some metric, and the dog images were close to the dog images with respect to the same metric, then you want those distance properties to be preserved as you go through this transformation. So even in the low dimensional space, you want the cat images to be close to the cat images and the dog images to be close to the dog images. You don't want to lose that. Let's visualize it. So let's say I have some points here. And if I look at these points, it looks like they're living in a two-dimensional space here. And my two-dimensional space is trying to just act as my cartoon for a much higher dimensional space, right? So I can't draw for you thousands or millions of dimensions. I'm just drawing 2 dimensions here, and I'm trying to go into a low dimensional space. And in this case, low dimensional is just going to be 1. So in reality, what might be happening is I might have thousands or millions of dimensions, and I'm coming down to tens or hundreds or something of that order. But here I'm just going from 2 to 1. And if you look at this purple line, it does seem to go through the data. So it does kind of catch a lot of the, it catches the trend line in this data. So maybe that makes sense. And the way that I'm going to bring the data into that low dimensional space from a 2-dimensional space to 1-dimensional space is I'm going to project them onto this line. And when we need to do this later on, I'll be very explicit about how to do that. But here you can just visualize these points kind of landing on the line. So they just kind of fall onto the line as if that were the new axis. And then I just have these new blue points. Okay, so now I have this 1-dimensional data set, and that's where I'm going to now train my algorithm. So my new transformed examples come from this 1-dimensional line now. These blue points will serve as my new examples. Okay, let's kind of wrap up by thinking about a case study that's going to help us move towards our project. So we're going to think about binary classification. Okay, and so what's our goal in binary classification? It's to come up with a good decision rule. All right, and so think about a data set, and this data set is going to just have 2 features, just so I can draw it. So it's going to have x1 and x2. And so for each example xi, I have the coordinate xi1, that's its first dimension, and I have the coordinate xi2, that's that example's second dimension. And each example also has a label. We're going to write as plus minus labels, meaning that yi is either +1 or -1. And the reason we like to do that is it's, again, easier to visualize this without having to draw a 3-dimensional plot. Okay, so I'm just going to draw my data set for you here on this plot. So I have pluses and minuses kind of sitting here. So let's say that this is the data set that I'm given. And here's one possible decision rule. We're not trying to, do anything formal here. I'm just drawing some line, and I'm going to say that on one part of the line, the blue part, so above the line, I'm going to decide plus, and below the line in this red part, I'm going to decide minus, okay? How can I actually measure my performance? So what is a good performance measure? Well, one way to do this is with the error rate, okay? And this is just going to be the fraction of mixed classified points, the points that I make the wrong decisions about. Okay, so in this example, I have 12 examples. So if you count the number of red and blue points in total, I have 12. The number of mistakes that I've made with this decision rule is 2. This plus and this minus that I've circled in orange, those are wrong. So they are on the wrong side, so I make the wrong decision. I incorrectly say that this circled plus is a minus, and I'll incorrectly say that this circled minus is a plus. So those are 2 errors. And so my error rate is just going to be 2 divided by 12, and that's about 16.7%. And this is often reported in the literature in terms of percentages. We're used to dealing with probabilities, but it's good to stay with the convention so that we can understand other things that we see in the literature. Okay, so one way to do this, and there are lots of ways to approach this problem, but one approach that we might come up with now is to say, well, let's try to estimate the conditional probability models. Okay, so the conditional probability models in this case will be f of x given y when y is positive, and f of x when y is negative. Okay, and if we had those, we could just apply the ML rule. That's a sensible way to try to solve this problem. So, how can we actually estimate the probability model from the data set? Okay, so one thing that we've actually thought about before is the parametric approach. So the way that I would do this is assume that the data comes from a particular family of random variables, okay? And then I just need to estimate the parameters from that family. So this is nice because it actually converges pretty quickly. I just need to learn the parameters, but maybe I don't have the best fit because it's the wrong family of random variables. Here's an example. Let's assume that the random variables are going to be Gaussian. Okay, so then I just need to learn the means and the variances from my data and plot the resulting distributions. So here, what I've done is I have 8 blue points. It's kind of hard to see them down there on the x-axis, and I have 8 red points. So this is a 1D example. And so I've calculated the mean for the blue points, calculated the mean for the red points, calculated the sample variance for the blue points, calculated the sample variance for the red points, and I drew the resulting Gaussian distributions, and then I can make my decision using the ML rule and picking the decision that has the highest likelihood as usual. If I get more and more data, I'll get a better and better estimate of the mean and variance, and maybe I get a better decision rule. So you can see here, before I had 2 very different looking Gaussians, and now it turns out that they look more similar, which actually, for the way that I've generated this data, is correct. Those distributions are just shifted over by a mean. So it did catch that. Now, another way to deal with this is a non-parametric approach, and to try to make very few or no assumptions about the distribution family. And this will converge much more slowly than the parametric approach, but it will get a better fit in the end. Now, this is its own subject, so I can't do this justice in just 30 seconds, but I want to give you a visualization to help you understand what this means. So we're going to just visualize what kernel density estimation would do. It tries to place a kernel or a little function at each point that you have in your data set. Okay, so for instance, this function estimate is the average of my points, and for every point, I place a shifted version of a function. Okay, so in this plot, you can see what I've done is I've summed up a lot of these little functions that look like tiny little bumps. And when those bumps overlap, I get kind of this bumpy surface. And maybe if there's no point for a while, it kind of falls off to 0, and then I get another bump. And then I take this to be my estimate of the distributions. And I can make my decision rule, my ML rule, based on that. And honestly, in this example, it looks kind of the same. So maybe ultimately I got a very similar looking decision rule, just in this example. If I get more data, I'll get a better and better approximation of what I have. And you'll see here that I actually found my way to a estimate of the distributions, it looks quite different from the Gaussians that I have above. And this, for the data set that I actually have, it turns out to be a better fit because I generated the data, I know what the underlying distribution was, and I know that this is a better fit. So I did eventually capture that. But maybe for making my decisions, it doesn't really matter. Both of them, if you look at these plots, would have made the same ML rules, more or less. Okay, but there are situations where the parametric and non-parametric approach would lead to different decision rules. Okay, well, here's another way to think about this. Is there some way I can actually improve on my error rate for this simple decision rule? So remember we had this purple line and I had a 16.7% error rate. So could I come up with a decision rule that's better than this? Well, actually, yes, it's easy to come up with a better decision rule if I'm just thinking about it naively. And I can always actually get the error rate all the way down to 0. One way to do that is by memorizing the data set or by designing a more complex decision boundary. Okay, so here's one. So here's a very complex decision boundary. And you'll see what it's done is it's drawn this curved orange line. And on one side of the line, let's say the left side, I colored in red. That's where I decide minus. And on the other side, the blue side, that's where I decide plus. And okay, that's great. I now have no errors. Okay, so on my data set, I'm making no errors. And so my error rate on my data set is now 0%. So what's wrong with this? Seems fine. It seems great. I managed to get 0% error. But maybe what I'm doing is maybe I'm overfitting my data set. And if I were to apply this resulting decision rule in the real world, maybe I'm going to get some performance that's lower than I might expect. Okay, so here on this plot, I'm going to draw a bunch of new examples that we're imagining come from the real world. I've kind of put this decision rule to operate in the real world and get more examples. And we're going to see where the green ones lie. So the green ones, I have lots of pluses and lots of minuses. And if you look at these new data points, it turns out that the simple decision rule that I have is better. Okay, now that's just because I designed this example to have that property. You can see that there are a lot of green minuses that fall into the blue region given by the complex decision rule, and that's bad. So it makes a lot of errors on these new points, and it also makes a lot of errors on the pluses. And if you look at how the original simple decision rule would have dealt with this, that would have made many fewer errors. Okay, so that's just for this simple cartoon illustration. The main point I want to make here is how do we know that we are not overfitting our data set? Okay, that's the thing I want to avoid, right? So I don't want to try to infer behavior that's not really there just based on a couple of random points in my data set. And the most commonly accepted approach for dealing with this is to, so what we want to do is avoid overfitting, is to split our data set into a training data set and a test data set. Okay, so training data, that's the data that I'm going to use to help me select my decision rule and optimize all of its parameters. What do I mean by optimize its parameters? Well, for instance, if I was trying to fit a Gaussian distribution, I would only use the training data to get the sample mean and the sample variance. Okay, here's my training data. This is a different 2D example, and I fit this decision rule. Okay, so I came up with this boundary. It does make a couple of mistakes, but that's going to be my decision rule. I'm also going to have my test data. Okay, so my test data I'm using exclusively to estimate the error rate of my decision rule. The reason I need this is it helps me compare different approaches, okay? And it's important to note that I'm not really allowed to use the test data to optimize the parameters of my decision rule. So I cannot incorporate the test data to go and estimate sample means and variances that I would use to build the decision rule. That's not allowed. I can only use it to try to estimate the final error rate, okay? And maybe compare totally different approaches to designing a decision rule. And the point of this is I'm trying to mimic what I might see in the real world, which is that I will get new examples that I'm not allowed to use as part of my decision rule design process. Okay, so here I'm going to reveal in green some test data. So I get these pluses and minuses. So the key thing to note is that these blue training data and green test data all come from the same original data set that I've split into two parts. So the training error rate, that is going to be the error rate that I've calculated only on my training data. So I, in this case, have 10 training examples, and I made 2 errors on my training data set with this decision rule. So my training error rate is 2 over 10 or 20%. Okay, the test error rate is going to be the error rate calculated exclusively on the test data. In this example, I have 6 test points, and I make 2 errors on them. I'm circling those, and therefore my test error rate is going to be 2 over 6 or 33%. And this is kind of illustrative of what you will see in practice, which is that you'll typically have a higher test error rate than your training error rate, because no matter what you're doing, the training error is sort of benefiting from the fact that the decision rule is customized towards the training data that you have. And so the test error is hopefully giving you a better signal about what you will encounter in reality. Again, there's a lot of interesting variations on how to use training and test data and how to split it up and kind of do that in a way that you can get a better and better estimate of the error rate and optimize the parameters in a more efficient way. This is just to overview for you the basic idea, and there are a lot of interesting resources and classes to take on machine learning where you can understand more.